The other beautiful example are the nuclear galaxies. And here is the center of our own galaxy, where we've got some utterly remarkable observations of stars moving in orbits about the very center of the galaxy, about the black hole. Now, if all of this works, I will show you now a video of that happening. I will go here, and I will go to Open Recent, and I will go to Orbits. Now, this is going to show you the orbits of these infrared stars about the black hole in the center of our galaxy. This is observation. This has actually been seen by Reinhard Genzel and his colleagues. And we get the three-dimensional information. That star S2 gets within 17 light minutes of the black hole. 17 light minutes. Remember, it takes 8 minutes for the light to get from the sun to us. That's how close that star is getting to a black hole. So these are absolutely fabulous observations of what's going on. Now, let's come back to there. And in fact, from that you can work out the mass of the central black hole. It turns out to be about 2.6 million times the mass of the sun. So that's another wonderful object to study for understanding the nature of black holes, and indeed testing the theory of relativity itself, general relativity itself. And now we know that in most massive galaxies there are massive black holes present. And these are just 4 examples in which the case is absolutely convincing that we've got black holes with masses, in the most extreme cases, of about 1 billion times the mass of the sun. Now, one final thing about the black holes before we move on to the next part, and that is, how can we actually study matter in these intense gravitational fields? Now, one of the most remarkable stories is the ability to see radiation from almost the last innermost radius above the black hole. Now, these disks emit reflected X-ray emission, and that can act as a diagnostic tool for what the dynamics are. So, here's looking down on the disk from above, and there's this wonderful fluorescent line about 6.4 keV here, which, if it was just you can see this from the disks of these things, but you've got to add on some extra things because it's in such a deep gravitational field. You have to add in the general gravitational and the relativistic Doppler shift effects. Now, I thought you'd like to see what a black hole with a disk about it would look like if you had extremely high resolution eyes to look at the X-ray emission. And these are cases where we've got no rotation, Schwarzschild black hole, maximally rotating black hole here. But I want to show you now, this is an example of the bending of space-time. Right? Okay. So here's how it goes. So here are some calculations by Yuri Dabrowski showing that little bit of the black hole. And you may ask, where do all of these bits come from? And it's all due to the bending of space-time about the black hole. So here, that bit sticking round the bottom, that's radiation which starts from the far side of the underside of the black hole, is bent round the black hole and comes off towards the observer. And it's because of this bending of space-time that we can see the underside of things. Number 2, that line there, that little ring there, that starts on the upper near side, goes round the black hole and speeds off towards the observer in that direction. Number 3, that starts on the underside of the near side, goes round the black hole and comes to us. And then finally, number 4, it starts on the upper side of the far side, goes round the black hole, comes off towards us. Now, that's all showing the extreme bending of space-time about the black hole. Now, of course, you can't see that. But, of course, the important thing is they will suffer different amounts of red shifting or blue shifting depending upon where they come from. And so the spectral observations are very important. If you now ask what are the effects of that upon that line, you get a rather characteristic shape which looks like this. So if we now use the XMM experiment to look at the spectra of these objects, here's an example of this line from this galaxy with a very unmemorable name, MCG -6, -30, -15. But it's an incredible observation. Here is the original line, and here is the radiation being redshifted to very low energies. And what that tells you is that this radiation from here must be coming from the innermost region of the black hole. It's the innermost edge of the disk which is the most strongly redshifted. Absolutely fabulous observations. So you can see we can diagnose strong gravity using black holes. Now, part 2, dark matter. How are we doing, Alan? We are 50 minutes. Okay, off we go. So, what about the dark matter story? Now, the galaxies are the building blocks of the universe, and they come in these forms, either spiral galaxies or elliptical galaxies. But there are weirdos in the universe, and this is one example here, the Antennae Nebula, where it looks as if these colliding galaxies have grown tails. And you ask, how can we do that using normal gravity? Well, the answer is, if you arrange your dynamics correctly, you can explain even these strange phenomena. Let's just have a look and see what this simulation by Simon Pike looks like. Here's ordinary galaxy rotating as a beautiful spiral. Along comes friend, on its carefully chosen orbit, and then they strongly interact gravitationally and disrupt the beautiful spiral structure. Lots of star formation takes place. They're on bound orbits, so the two beautiful spiral galaxies come together to form, well, yes, you understand, a bit of a mess. But almost certainly this is going to end up producing elliptical galaxies out of pairs of spiral galaxies. Now, what the important point about this is you will notice that these big long tails, they appeared absolutely naturally, and that's because they were coming on rather carefully chosen resonance orbits, so that the galaxies are rotating in the same direction as their local speed that they pass each other, and then gravity acts to pull out the outer layers into big, big long tails. See the beautiful tails. If you look at the right angle, you will see the antennae. So, that's very good. You can also explain these sorts of weirdos here. Galaxies shouldn't do this, a ring of blue stars with a funny thing in the middle. But if you've got a supercomputer, you can drop one galaxy through another, and you will produce this. Here we go, through the middle, bullseye through the middle, and out we get these ring of stars, and look, we've even got the spokes in the structure. In other words, gravity can produce all of these pathological-looking structures on its own. Now, gravity does other things. And the conference that has been going on, which sadly I could not attend, is all about the discovery of cosmic shear. And that really means the shearing of images by gravity. Massive objects, galaxies, clusters will shear objects. And this is one of the most beautiful images taken by the Hubble Space Telescope through a cluster of galaxies, but also look at these wonderful arcs. And these arcs are the images of very distant galaxies which are being lensed by the mass in the cluster and by the galaxies. So here's just illustrating what happens. We have a very distant galaxy. Light is bent because of the bending of space-time. Bending of space-time is everywhere in this story. And you can see here's the bending of space-time, which means that we see the same object from many different directions, and that accounts for these beautiful arcs that we see in these images. And just to show you the sorts of thing that happens, here's an exaggerated view of the bending of the images of background galaxies by galaxies in a cluster. This is due to Tony Tyson, but I think it's rather fun. If we simply let the program run, you will see how the background galaxies are all being distorted as you move the cluster in front of it. Do it again. You see, galaxies which look very nice are being bent and distorted all over the place. And the clever thing is to use these distortions to work out all the mass within the systems. And that's the importance of this. That in fact, when you reconstruct the mass distribution, you can do that independent of knowing where the galaxies are, and you will find where all the gravitating mass is, the mass which is present in this large cluster. And the answer is that most of the mass is not in fact in the visible bits of galaxies, but in the space between the galaxies in the cluster and in the halos of the clusters. That's where the dark matter is sitting. Now if we go up a further scale in the universe, here is again a picture of the universe on a very large scale, with us in the very center of the diagram here, looking out into the universe. And you'll see that it's a pretty irregular looking picture. If the galaxies were uniformly distributed in space, the points would be uniformly distributed over that diagram. And you can see that's not true. There's things like this great void that we see here, and there's things like this great wall of galaxies. A cluster of galaxies that we saw last time would be, for example, just one of these dots there. So this is a picture of the universe on the very grand scale. And if we go out further, again, we still see the same distribution. And many of the people in this room who've been at the conference have used the results of the Anglo-Australian Telescope 2DF survey to push that out even further, way out 5 times further. So the last picture was there. Now we see this sort of structure going way out in the universe.